Hello everyone, today we'll talk about the problem number of steps to reduce a number in binary representation to 1. We're given a number and we want to conduct the following process for as long as the number is not equal to 1. If it's even, we want to divide it by 2, and if it's odd, we have to add 1 to it. The number is presented, because it can be quite a big number, as a string with binary digits. And we have to say just the number of steps that's necessary until we reach 1 starting from that number. So for example, if we have a number like this, and let's say some zeros, well, then first the number is even is the same as saying that it ends in a 0, so in one step we remove this 0, another step we remove this 0. Now here we have to add 1, so this changes into a 0, and this changes into a 1, so this is a single step. Then the fourth step is to remove that 0, and again, the number is odd, we have to add 1, and so on. And we have to report the number of steps until we're left with only a 1. Or in this case, the 1 would be here, in our imagination. And we have to report the number of steps, and of course one way to do that is just to simulate this process. If we're using Python, then it's actually very simple, because Python has big nums by default. So we can just take the string, convert it into a binary number, so convert it into a number, interpret it in base 2. And for as long as we're not at 1, we have to make a step, and that step is, well, what it says here. If the number is odd, so this is a way of seeing if the number is odd. You can of course write it in a more normal way using modulo operators. Then we just have to add 1 to it. Otherwise we have to divide it by 2 or bit shift it to the right by 1. So those are just fancy ways of saying this number is odd, this number is divided by 2. And of course, if we weren't using Python, we didn't have big nums by default, we could do that simulation in some other way, more manually. In particular, a similar idea would be to just try to simulate it by going through the string backwards, because what we have to remember is the number of steps that we've made, of course. And we either make just the single step if the number is even, or we make 2 steps if the number is odd, add 1, the resulting number is even, so we divide it by 2. And the idea is that the number will be odd, of course, if we have a 1 at a given position. And also if we have a 1 at a given position after, well, so let's say we have a 1, we have to add 1 to it, so we have to carry over that 1 to the next column, to the next position. So we just remember if we carried it as in normal addition, and we remember to add the carry to our current digit. And then if the digit plus carry, the digit being equal to 1, or carry, exactly one of those, is true, then the number is odd and we have to do another operation. And of course what we can, so this is a simple just simulating the process. And at the end we have to return the number of steps. Plus we have to also remember if the carry is on, because that means that we have also to make another step outside of our number. And what we can notice here, which is quite interesting, and this is indeed true, is that we can set the carry to 1, but it never gets set back to 0. And this is indeed true, because if at some point we see the 1 here, and we have to add 1 to it, then this flows to the next position. If that next position was already a 1, then it now becomes a 0, and of course we still have a carry, so the carry is still on. And if that previous position was a 0, then our carry makes it into a 1. But now if it's a 1, then we have to add 1 to it, so still the carry is on. So once the carry gets turned on, then it will remain on for the rest of the algorithm. And if we want to get a little bit fancy, we can then consider what it means actually for the number of steps. And this would be, let's say, a shorter way of implementing it, just based on this observation that the carry gets turned on the first 1 from the right, and then remains turned on for the whole algorithm. So we're interested in counting the trailing zeros, so where the first 1 is going from behind, from the right. Also how many 1s there are. And then one way of reporting the result without simulating if we have those 2 numbers calculated would be something like this. So you can consider this in your free time, and perhaps you can come up with a simpler solution. So yeah, pop count is the number of ones. This is how many trailing zeros there are. This is of course the length of our number. And this just tells us if we have more than one 1. Because if there is only a single bit set in our number, then the process is very simple because we just remove all the zeros and that is the end. So the carry never gets turned on. So that's why this part is important.